Before I start, I do have some interactive demos later on. So if you want to grab the URL, if you like playing with sliders on your own, you can do that. It'll just link to the slides, but then there's more links later on. All right, so first, real quick, a little bit about me. I'm trained as an experimental psychologist. I'm right now a postdoc at Cincinnati Children's Hospital in the Division of Sports Medicine, and that's where the research I'll tell you about today came from. On my way out, though, I'm co-founding a soccer analytics startup in Spain. I'd love to share more about it, but it would have to be offline, so please come talk to me. We're probably hiring soon. All right, so let's jump in. What we'll do today, I'm going to tell you some theory. So a little bit different than usual PyData talk, but I think it sets up the Python stuff that will come later. The theory of direct perception, some philosophy of mind. And I'll talk about dynamical systems and how to model them and how to explore these systems, specifically using bokeh applications. And then I'll do some massive simulations. They're massive for me, maybe not massive for some of you, but massive from anything I've done before. All right, so if you took intro to psychology or cognitive science in undergrad, maybe you encountered this type of problem before. If we get a rectangle on our retinal image, how do we know what shape really produced it, right? It's ambiguous. It could be any of these different parallelograms. And traditionally, the answer is we make some guesses. We maybe have some assumptions from our knowledge about the world. We get some hints, do some computation, and we take a stab at it. And this leads to a view of the mind where the order of operations goes something like this. We receive some sensory input. It's really bad sensory input. It doesn't tell us a lot of information. We have to process it. We have to apply some computation. And the objective of this computation is to construct an internal model of the world. And once we have this internal model, we can use it to plan our actions, which we then execute. And this leads to a way of thinking about cognition and perception specifically, where we're not really in contact with the external world. We're only really in contact with this model of the world that we build in our heads. And so we kind of have these lo-fi sensors. We're like trapped in our brains. We've got like some levers and pulleys. And that's really our only way of interacting with the world. And so that's indirect perception. Still pretty mainstream view in psychology. Now the alternative is direct perception. Obviously it had some philosophical antecedents, but really was made scientifically viable by J.J. Gibson in the 50s, 60s, and 70s. Gibson reframed the problem. Says, why we focus on the retinal image, that's not the input to the system. Instead, we should look at the optic array, all the light that's bouncing around the room at any moment. And we sample this array by a moving point of observation as we move through the world. So we have these angles, these visual angles to objects that change in reliable, systematic ways. And these movements more generally create what we call optic flow, how each point in the environment changes in the visual field. And there's reliable information in the optic flow. For example, a stationary point tells you you're on a collision course, and of course this is being used for autonomous vehicles, among other things. He also reframed the objective of perception. Maybe it's not necessarily to construct a 3D representation of the world, but rather just to discover the possibilities for action. So we don't need to know how many meters wide the doorway is. We just need to know it's the kind of opening that you might be able to walk through. So we reframe the input. It's richer than we thought it was. We reframe the objective. It's easier than we thought it was. So we don't need hints. We don't need cues. But we get mathematical regularities or invariants that specify the state of the world and specify our relationship to it in a reliable one-to-one manner. It doesn't require any further processing. So good news, if Gibson is right, we're not trapped in our heads after all. And then our job as perceptual scientists is to kind of figure out what are these invariants, what is the information that we're using to guide our actions. So that brings me to perception in action. Take a traditional problem in this area of how to catch a fly ball. So how do we know how to get to the right place at the right time to catch a projectile? Now the computational approach, right, would say, all right, we observe the location of the ball, its velocity. We have some internal model of physics based on some assumptions. That allows us to compute the future trajectory, get to the right place at the right time by executing some motor program. Easy, right? Well, there's an even easier way if we consider the optic flow pattern that the fly ball makes from a moving point of observation. In particular, if you move in order to cancel out any optical acceleration, so the visual angle of the ball, don't let it accelerate, you'll get to the right place at the right time. So if it's accelerating upward, you have to accelerate backward. If it's accelerating downward, you have to move forward. And if you do that, it's just a moment-to-moment strategy, doesn't require any prediction. If you do that, you'll end up in the right place at the right time. Or I guess, at some point you have to actually catch it, or it'll just hit you in the eyeball. And so more generally, then, we like to think about movement and perception as linked, or perception and action as intrinsically linked. So movement generates information via optic flow, at least for vision. And then this information parameterizes the movement. So it doesn't make sense to talk about the perceptual system and the action system, but we have to think about perception and action together. But I'm a math nerd, so I like the formalism. So we think about the environment as a dynamical system governed by the laws of physics. And we try to figure out what are the laws of control that govern the agent's behavior. And these control laws are a function of the information, which is itself a function of the state of the environment. And then the environment is modified by the actions of the agent via forces. And then based on some ideas about self-organizing systems, there emerges some kind of stable behavioral pattern from this interaction. And we study that using behavioral dynamics, which is what I will share with you next. So I'm going to switch gears a little bit, show you some dynamical models. First one is the HKB model. So this is a coupled oscillator model. And what I find really cool about this is it's domain general. So it doesn't matter what oscillators you have. It describes two metronomes coupled physically by an unstable surface. Describes crickets chirping in synchrony. And this is a classic experiment in perception action. Coordinated limb movements or finger wagging. And even if you have participants in rocking chairs, ask them to synchronize by looking at each other. You get with all these cases, you get the same kind of global patterns of the possible outcomes. So as long as there's some kind of coupling, it can be physical coupling by vibrations, can be informational coupling by perception, or neural coupling through one person's body. And here's the actual model. And perhaps the reason it's so general, it's just two terms of a Fourier series. So if you've never seen a dynamical model before, you got the state variable on the left, or specifically the rate of change of the state variable. And so what the model tells you is how does the state of the system change as a function of the current state. So in this case, it's a one-dimensional system. There's one state variable. In this case, it's relative phase. So when relative phase is 0, that's in-phase movements. So like your limbs moving together, for example. And then at pi, it would be anti-phase, so moving in the opposite direction. And based on the current phase of the system, the relation between the two oscillators, you get a sense of how the phase is changing at the moment. And in this formulation of the model, we have two parameters, coupling parameter B and delta omega, which is the difference between the frequencies. So this lets us model when you have two oscillators that prefer to run at different speeds. All right, so I'm going to switch now to the actual demo here and try to walk you through this. So what we see in the top is the phase portrait. So this is just plotting the equation of the system. We got the state variable, relative phase on the x-axis, and its rate of change on the y-axis. And it's a one-dimensional system, so you can imagine its movement as just moving back and forth along the x-axis. The state is just a position on the x-axis. So wherever you start, there's only two things that can happen. You move right or you move left. And the curve tells you how you're going to move. So for example, see if you can see the cursor. Yeah. So if you start over here, the rate of change is positive. You move right, you end up here. If you start over here, rate of change is negative. Move left, you end up over here in this same spot. So anywhere where this curve crosses the x-axis is a fixed point. If you start on a fixed point, you'll stay there. If it's a filled circle, it's an attractor. If you start near it, you'll end up there. The open circles then are repellers. If you are exactly on it and there's no noise, you'll stay there, but as soon as you come off of it, you'll head in one of the other directions. And then on the bottom, another way of looking at the same system is by the system potential. And this is just the negative integral of the equation. And now the attractors are valleys and the repellers are peaks. So in this way of representing the system, you can think about, from wherever you start, you can think about a ball rolling down a slope. So it'll end up in one of the valleys. And now what's interesting is how the system changes as we change the parameters. So first, how it's set up now. We've got two stable behavioral patterns. So 0 and 2 pi, they're the same. It's a circular variable. That's stable at 0 or at 2 pi down here. And then at pi, that's also stable. Then if we change this coupling parameter, we see what happens. If you look at, I'll go back and forth a few times so you can look at the top, you can look at the bottom. So you get the valley turns into a peak, and vice versa. Or you get one fixed point kind of splitting into three. Same thing, really. So now that when you're down in this regime, you just have one stable pattern. And then see what the other one does. When you add this difference in frequencies, there's some asymmetry in the system now, and it actually changes the relative phase that's stable. Is near in phase, but not exactly in phase. And that's the kind of pattern that you'll observe. Now, the nice thing about dynamics is there's some pretty simple rules. Since it's a continuous line, you have to have, if you have two attractors, you have to have a repeller in the middle, for example. And as a result, there's only so many different things that can happen. So there's only so many different ways you can transition from one type of behavior to another. You can have like this one, where you get kind of two fixed points coming together and eliminating each other. And you can get this kind of transition where one fixed point becomes three. So you have a really limited repertoire. Any one-dimensional system, as long as it's a continuous equation, those are the only different things that can happen. All right, so let's head back for a minute. I want to, you can check out the code if you're interested, but want to definitely shout out to all the libraries that make this possible. So Bokeh Apps is a huge part of it. Makes it really easy to make this kind of interaction. And then SymPy is great because you can interact with the equation symbolically. And then when you want to evaluate it, you convert it to a NumPy function. And then that lets you do things like the potential in this case is the negative integral, as I mentioned. So you can let SymPy handle that for you. So if I wanted to change the equation, add another parameter from a different version of the model, it's pretty easy to do that. You can solve for the roots. So with SymPy, you get the symbolic computation, but you can also still use it for fast numerical evaluation. All right. Go to the next one. So here we have a Van der Pol oscillator. This is a type of nonlinear oscillator. It does have some physiological implications, but let's not talk about that. So in 2 dimensions, we can think about the state of the system, right, as any point in the xy axis in the Cartesian plane here. And then a trajectory is like a curve through that space. So let's start with k negative. You can see the phase portrait. It kind of shows you any point you would start at, what direction you're going to go next, which is really all the system is defined by. And then I have it set up thanks to bokeh, where you click on the system and it does a simulation. All right, so here we have some damping going on with this oscillator. It's going around, but it eventually ends up in this fixed point in the middle. Or if you start further outside here, you zoom out to infinity. All right, let's go the other way. So now, with k, when k is positive here, we get a stable oscillation that's kind of self-sustained. If you start inside it, you'll go back out. If you start outside it, you'll head back in. And so in 2 dimensions, you can have fixed point attractors. You can also have what's called a limit cycle. So it's still an attractor, the eventual final state of the system, but it's a set of points instead of just one point. And again, in 2 dimensions, there's a limited repertoire of different things that can happen. It's a little harder to see those transitions in this app, but you can get one fixed point turning into a limit cycle and vice versa. You get different ways that the attractors can interact with each other. But there's only like a handful of different things that can happen in any 2-dimensional system. And what dynamics really are useful, it's not like some of the other models we talk about here at PyData, not necessarily for making a prediction or explaining what's about to happen next, although it does do that. But what I find it useful for is describing all the possibilities that a system has. So in this case, we know there's really 2 regimes it can be in. It can have the fixed point in the middle, or it can have a limit cycle attractor with a continuous oscillation. And you can kind of see what the transition looks like between those 2 things. And that's why I like to do many simulations instead of just one. Get a sense of all the possibilities of the system. All right, one more. We'll point out the implementation details. Again, I'm using SymPy. And now to do the simulations using SciPy's solve IVP, solve initial value problem, which takes the differential equations and just runs them through. Again, not too hard once you have the equation. All right, one more. This is the steering dynamics model. This is the main model I've been working with. So this describes how a person or an animal or any locomotor creature is navigating through an environment, avoiding obstacles, and trying to reach a goal. And the equation here describes the angular acceleration of the heading. So it's basically like an analogy to an angular spring. So you can imagine there's a spring pulling your heading toward the direction of the goal, pushing you away from obstacles. And so we have, in this case, it's a 4-dimensional system. When you write it as a series of first-order equations, you have heading, you have rate of change of heading, and you have x and y. All right. One more. So now it's a 4-dimensional system, as I said. So here on the left, we have a phase portrait, which is, in this case, a 2-dimensional slice of this 4-dimensional space. I don't really have time to talk about exactly how to interpret that. Let's focus on the plot on the right, which is just a top-down view of, right now we got an agent, an obstacle, and a goal. Select this tool. Now, thanks to bokeh, we can move these things around. This is really easy to set up. And let's just see what happens. So I have it set up right now. When I press sim, it just does 8 equally spaced starting trajectories, and then simulates the trajectory from there, going around the obstacle to a goal. We can double-click on the plot, and add another obstacle. We can kind of see the possibilities there. So can kind of experiment with how close do I have to get, for example. How close do I have to get to that gap before it actually takes it? There we go. How close do you have to get before it always takes it? So these kinds of things are useful for designing the environments and the experiments, which I will show you next. And again, it's not necessarily useful for exactly what the person will do. Like in this case, actually it's colliding in one of those simulations. But it's useful for understanding all the possibilities for action. When does the gap disappear? When does it not become the type of route that someone will actually take? And here I'm adding one more tool from SymPy. I'm compiling the equation. Every time we add an obstacle, it's programmatically generating the equation. So just adding some more terms on to add other repellers from the obstacle. And compiling that to Fortran so that we can simulate it more quickly. And then still the simulation itself is with SciPy. All right, so now finally, I'm going to show you some data we collected in the lab. There's some simulations at least based on this data. So we have an augmented reality and virtual reality laboratory. This specific data is from a study we're trying to design scenarios to train young athletes to be more aware of their surroundings to prevent unanticipated collisions, which are a big source of concussions. So here, this is augmented reality. Got some product placement. That's the Microsoft HoloLens. So that's projecting obstacles into the lab space, and then their task is to dribble around them. And then here's a VR trial. This is obviously from the participant's point of view. In this case, there's no dribbling. They're just trying to avoid the NPCs, which are trying to reach them. You can see that cursor is showing our eye tracking data. So we have eye trackers embedded in the headset, which we try to understand the scanning behavior as a big part of unanticipated collisions. Also see the safety features, that stop sign wall, to make sure that in VR they don't get too close to the actual physical wall. All right, so here's the final thing I'll show you. It's not really good scale for the presentation. Sorry about that. So what I'm doing here, this is the same trial. Got the agent trajectory in the white there, and then the red are the obstacles, or the NPCs. And here we're using SymPy to programmatically build these equations. In this case, we have a 4-dimensional system for each agent in the scene, including the NPCs. In the simulation, at least, they're guided by the model. And the equations are really long. You know, they're treating the other NPCs as obstacles. So you can just generate that programmatically. If you're a masochist, you can print it out. It's super long and crazy. But anyways, altogether, that makes a 20-dimensional dynamical system. And here we're performing 2,500 simulations at each time step. And it's a deterministic system, so I'm randomly varying the starting position at each time step, and then using these hex bins in order to see the likely future positions. And so that lets you understand kind of where there's a second solution that emerges for a moment. In this trial, they kind of take the most predicted solution most of the way through. You kind of see when they're being funneled into one trajectory, when there's more options open. This runs in a few minutes on a single core, so there's still, of course, more optimizations I could do. It's not parallelized yet. But it really blows my mind how far we've come thanks to really all the open source projects that we use. So when these models were first being made, like 15 years ago, what they would do, just to compare the model to the data, they would actually average all the data they collected into one trajectory and then simulate it once. And now not only are we simulating every trial individually, but we're doing this kind of thing for each time step. And we have some ideas in mind for how to use this in our environments, for example, to guide the NPCs, to funnel behavior in a certain way, create easier or more difficult scenarios. But we got to get that down to real time first, so that's the next challenge. Yeah, I guess that's about it. So thanks to Adam Kiefer, my advisor, for getting grant money, making this possible. Ryan McPherson programmed the Unity environments for AR and VR. And thanks to all of you, and thanks to everyone who made all these libraries that we're so lucky to be able to use. Thanks.
Yeah, so now we have a few minutes for questions.
I didn't quite understand how like those AR and VR environments related to the simulations that you had. Were you trying to confirm that like people behaved in the same manner as your simulation?
Well, so first of all, the model itself comes from similar VR studies that were done by another lab, like 10, 15 years ago, as I said. In our case, we're using the model to control the NPCs and to predict the likely outcome. So for example, doing the simulations just from the starting position, from a range of initial conditions, we can see how many possible paths there are, get a sense of which scenarios are more difficult or easier, get these different metrics of them. And the end goal is to design a training set that we can kind of ramp up the difficulty to train better collision avoidance behavior. So still the first stages in terms of that end goal, but it basically allows us to assess the environment. The models are, so there's similar models out there like the social force model that do locomotor trajectories. This one, unlike the others, is based on human data. But in this study, we're not actually fitting it. It's already a fit model.
Just curious, like, how convinced are you that this really explains how we behave?
I think up to a certain point, it's pretty powerful. I mean, it gets more philosophical. I think when language gets involved, certainly that changes things. Maybe that's why I stick to perception and action. I think as far as movement, I mean, animals can do this stuff. I think it explains it pretty well.
Hi. When you solve any ODE, usually there's numerical instabilities.
Yeah.
Do you deal with that with SymPy, or how do you handle that issue?
Yeah, good question. In this case, it didn't come up. I guess just because the equation actually is fairly simple. There's no like explosions of denominators or yeah, that can happen in other models. I do have some other research I've done on a braking model, which is like how to use the optic flow to avoid collisions in terms of controlling acceleration. In that one, I did have instability problems, and I'm not really an expert in all the numerics behind it. I mean, that's the nice thing of all these libraries. You don't have to be, but I solved that problem by just kind of going through all the different solvers that SciPy offers until I found one that worked, reading the documentation to get a sense of why that's the case or not.
Yeah, questions?
Thank you, and it was just very cool visualizations. Were there any like novel results or paths that were taken either by people or predicted by the optimized model that were kind of very like aberrant or?
Yeah, certainly. So one weird thing about the model is it is a constant speed model. So there's a speed component that we could use, but it still needs some work. So that creates weird situations where it's like if you got two people, one person trying to evade another person, and they're both doing a constant speed, you get like weird loops. So that doesn't happen, of course. Also, I don't have the limits of the lab on here, so some of the simulations go pretty far outside. And then finally, I guess sometimes I think people just have the participants come up with their own strategies. So, for example, pretty common. It all comes pretty fast, and these guys come at you quickly. So some of the participants just kind of run in a direction, the first direction they go, and then just try to beat them all around the edge. And I think that's the strategy they're coming up with before the trial even starts. So it's not really something the model can anticipate. Well, maybe. I'm not sure. But that's something I've tried to make it do. Yeah, good question.
Thank you.
All right then. Thank you very much.
Thanks.